Hey everybody, welcome to video 4-4. In this section we're going to be talking about perpendicular lines, and there are just a few theorems that we need to kind of highlight here. Not a whole lot of instruction needed as far as new things or things that aren't really like common sense, but I did want to walk you through and kind of highlight things along the way. So first off, for our explore here, and I'm on page 195 at the start of section 4.4, this shows you the different steps of constructing a perpendicular bisector of a segment, and we are going to be doing this together next time we see each other. But if you would just make sure that you read through this page, kind of get the idea of where the compass point should go, etc., and then also watch the very short video, it's only 3 minutes long, that's linked underneath this one on your outline. It'll kind of give you a live demo of what it is that we'll be doing with our compasses. Okay? So on the next page, page 196, a lot of this section walks you through the proofs of the different theorems. We're not so much going to emphasize the proofs, but you do need to be aware of what the theorems say, okay? So here in Explain 1, we have that a point is, if a point is on the perpendicular bisector of a segment, so that's the line, remember, that goes right through the midpoint and creates a right angle, then it is equidistant from the endpoints of the segment. Okay, so we're going to prove that in this example 1, and again, I don't need you to be able to duplicate the proofs here in the same way you were back in module 3, but it's good to know where it comes from. So if P is on the perpendicular bisector, here's point P, and M is the perpendicular bisector, then what we're going to do is to prove that this distance PA here is the same as PB, we're going to consider the reflection across line M, and then the reflection of point P, because P is right on the line of reflection, of course, you know that doesn't move, so reflection of P is also P, because P is on line M, which is the line of reflection, and also the reflection of point A across line M is going to be B. It's going to just reflect that same distance over, because it goes through the perpendicular bisector, and we know these distances are the same, so that's simply the definition of what reflection means. And therefore, the distance from P to A is the same as the distance from P to B, because reflection is a type of transformation that preserves distance. And remember, that's that idea of a rigid transformation that we talked about back in Unit 1. So again, if a point is on the perpendicular bisector anywhere along this line right here, then it is going to be equidistant from the endpoints of the segment that it's cutting in half. So that's the first theorem we need to be aware of. On the Your Turn on page 197, right here, 4 and 5, you guys are going to be using that idea of the perpendicular bisector theorem to find some missing distances. So take a pause on the video and let's do that now. The next part of this section 4.4 in Explain 2 talks about the converse of the perpendicular bisector theorem. So the converse simply says that if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector. So remember, converse, like we said, is just reversing the logic. On the previous page, we had a theorem that said if a point's on the line, then it's equidistant. This time we're saying if a point is equidistant, then it's on the line of the perpendicular bisector, or the line of reflection through that midpoint like we talked about. So what we're having here on page 197 is what's called an indirect proof. We are not going to be covering indirect proof in Geometry CP, so you guys don't need to worry about this, but I would just kind of highlight here our theorem a squared plus b squared equals c squared comes from, of course, our Pythagorean theorem, but I hope that you can see how that relates to perpendicular bisector if we think back to the diagram that we just drew on the previous page, where we had a segment and we had its bisector, And then we said any point P, remember, was equidistant to the endpoints. And of course, because it's a perpendicular bisector, that creates a right angle. And so in essence, really what we've created is two identical right triangles on either side of that line. You're going to use the idea of Pythagorean theorem here as you go through the your turn on page 198. And remember, a Pythagorean theorem says a squared plus b squared equals c squared, where remember c always has to be defined as that hypotenuse or the longest side of the triangle. Remember, that has to be in that part of the equation that's all by itself. So the legs squared added together equals the hypotenuse squared. And that's going to come in handy when we get to the top of page 198 here. You guys have a your turn, number 7, that you're going to be doing. Let's just put a couple labels on there so you can see where that Pythagorean theorem is going to come into play. It says AD is 10 inches long and BD is 6 inches long. And what you can see here is we want to find the length of this whole entire side here. BD is 6. What we want to find is the length of AC. Okay, so that's where we're headed for the your turn. I hope that you can see the right triangle. I hope that you can pick out which of the numbers that you've been given right now is the hypotenuse and feed that in there. Okay, take a pause in the video and just do that one problem, please. Okay, the last part of our video here is explain 3, and I did just want to highlight with you guys, we have a new symbol coming into play here. Our symbol is the perpendicular symbol, and that is an upside down looking T, but if I have it used in the notation, it means that two figures are perpendicular. Now obviously those figures have to be lines or line segments, but here's an example of what that might look like. Script letters with a perpendicular symbol in between means one line is perpendicular to the other, or possibly, as you see here, XY with a line over it, line symbol over it, is perpendicular to, and then it's possible to be perpendicular just to a line segment. So that's AB. So again, we're walking through some theorems about right angles. I'm hoping that most of these are self-explanatory for you, and it makes sense as we just kind of talk through the proofs here, but just want to highlight these two things. First off, if two lines intersect to form one right angle, then they are perpendicular and they intersect to form 4. So let's take a quick look at that. Given that the measure of angle 1 is 90 degrees, so we can put that right angle symbol on there. Watch what this statement has in mind. So first off, angle 1 is 90. 1 and 2 are a linear pair. And so if they're a linear pair, that means they're also supplementary by the linear pair theorem. And if they're supplementary, that means their measures add up to 180. Again, that's the definition of supplementary. We're going to substitute in what we know, which is that 1 is 90 degrees, and therefore by subtraction, 2 is also 90 degrees. So we'll put in a second right angle right there. Then, once we know that the measure of angle 2 and 4 are the same, because 2 and 4 are vertical angles, and that's the vertical angles theorem. So not only is 2 a right angle, but so is 4. And then as soon as we have that 4 is a right angle, we can say that the measure of angle 1 and the measure of angle 3 are the same. And so because angle 1 was 90, so is angle 3. So this is pretty straightforward. I think it makes sense. If one of them is 90, because we have straight lines and we have vertical angles, we're going to have 4 right angles there. So keep that in mind for the future. Then the second theorem on this page that you need to be aware of is part B, which says if two intersecting lines form a linear pair of angles that have equal measures, the only way that you can have a linear pair, that means they have a sum of 180 where it's equal measures, then that means that they are both 90 degrees. And so we read through this proof really quickly. By the diagram, 1 and 2 form a linear pair, so 1 and 2 are supplementary by the linear pair theorem. I'm just going to abbreviate that LP theorem. By the definition of supplementary angles, we know they add up to 180, and it's also given that we're told that the measure of angle 1 is the same as the measure of angle 2. And again, remember that's our given, so that can go right into our proof without much reason other than just saying it's given. So that's actually measure of angle 1 is plus measure of angle 1, because these two are the same thing. So, and that's going to equal 180 that's the substitution property. So if we add the like terms, that actually is 2 times the measure of angle 1 equals 180. And then with division property, we get that they're both 90. And so one is a right angle, and they're perpendicular by the definition of, and here's my symbol again, upside down T, perpendicular lines. So I want you to use those two theorems. If it forms one right angle, it forms 4. If we have 2 intersecting lines forming a linear pair, then with equal measures, then the lines have to be perpendicular. We use those two A and B theorems here as we finish off our your turns in this section. So number 9 on page 199 is next. And on this one, I'm not going to give you much guidance other than helping you label it. Look at what we're told here. We're told that B is parallel to D. That's this line right here and this line. Those are parallel lines. In addition, so is C parallel to E. So notice we have several pairs of transversals and parallel lines happening here. And then we're also told that the measure of angle 1 is 50 degrees. So let's put that on the diagram. That angle right there is 50 degrees. And that the measure of angle 5 is 90. So there's my right angle. Now remember what we were told, once it's a right angle between 2 intersecting lines, and notice the 2 intersecting lines here would be A and D, then somehow I've got 4 right angles coming into play in that bottom cluster. And we'll see what else that means. See if you can reason through that, and we're going to be looking for, in this your turn number 9, to find the measure of angle 4. Okay? And that takes us to the end of video 4.4, and we will see you guys next time.